Hello, and we're back. We should
Hello.
be in the clear. Hearing everybody, I mean. Um, of course, I'm coughing as soon as we start. So, we're hoping to keep this one short and sweet as well, much like the last one. And basically, what we're doing is we went through all the noisy data. We showed what effect it can have and why you would want to filter it out. And of course, we have nice, perfect data in the sim, so we're going to use it. I thought about implementing a Kalman filter inside the game. It looks a little bit, I don't know. It shouldn't be impossible. It just seems like it's perhaps a little unnecessary. Just adding unnecessary difficulty to yourself, if you will. If you guys want to see implementing a Kalman filter in Visi, let me know, and we can put it into a future show. But today, what we're doing is we are going to tune our lander for Luna, which is closer to uh, the moon's gravity, and we'll have a slightly different response to everything. And we want to make sure that our PID can land on Luna, and then we want to make sure we could land on Luna as if we were coming out of orbit, right? Because eventually we're going to take off, get all the way out to the moon, land on the far side, and have our thing out there saying hi to everyone. I guess I don't know what else it's going to do once it lands, but we'll figure that out later. Right now, so we're doing a couple of tests. Luckily, we have a fake moon to test on. Um, and I suppose all lunar landers, there's got to be somewhere out there a big, complex simulation of the moon that is readily available. I don't know if Google Earth is, I don't know how accurate that physics engine is. I know the physics engine here in the game is reasonably accurate. Um, but I did find a couple of odd things here. So let's get into it. I created a different data view that would be a little bit more interesting. So let's first just jump into the game, and I'll show you the minor changes done to the code here. If I can get used to moving on one monitor and watching on the other. So we I wanted we're still using the noisy code, but all the noisy multipliers are zero, so there's no actual additional noise. And then to start having some more information, we're putting out the sample number, and instead of the noisy altitude, we're putting out the velocity, vertical velocity, the altitude above ground level, the engine thrust, the fuel for the stage, the lateral velocity, which is how much we're moving to the side, also our nav heading and pitch. And the reason I added all these in there is in the future we want to do a little bit more control panelish. So anyway, grab this right quick. That's annoying me.
Yeah, I see it.
There we go. So in the future we want to do something which is I would refer to as data visualization for immediate action taking, which would be called a control panel. So immediate visualization of your data, like your speedometer in your car. It doesn't show you the history of your speed like these strip charts do. It shows you your immediate speed, and that's the kind of thing you would need to navigate moment by moment, like you do in a car. Of course, in a spacecraft, you do a lot of calculations, hopefully in advance, well in advance, of when you need to fire the engine, and then you fire the engine, and then you wait a long time as you coast. So, most of that immediate feedback, like we show them, there's a thrust gauge, um, and then your heading is probably only necessary while you're close to the surface, and then once you're out in the middle of deep space, going from planet to planet or what have you, then you're not really going to be looking at your gauges every single second. You're certainly not going to be accelerating and decelerating a lot. So we have pretty much the same parameters for our PID, which is our hover PID, which is 0.02, and it's actually a PD controller because we're putting in the proportional and the derivative, but we're not actually using the integral. And because the integral is the error times the delta time, and the derivative is the error divided by the delta time. I think this is why, as a PD controller, this works well for landing, but doesn't really work well for takeoff. So when we tried the other types of ascent, where we wanted to set our altitude at 5,000 and take off right for that altitude, we'd continually come under it, because and then we would slow down. Now, if we come under the necessary force as we're landing, well, we continue to go down, and so then the calculation continues. If we come under our estimate for takeoff, then we fall back down, and we get this, as you'll see here, overly strong response when going up versus coming down. And I think that's because we're using a PD term instead of a PI term, which is far more common for values that are going up from 0 to some number. But be that as it may, we're pretty much just going to take what we had flying on Drew and on Earth, which has the same gravity. And now we're just going to take off from Luna. We got all this extra data up here, so we've got a new visualization for our data. Let's save this. Start out towards the spacecraft launch. And while that's going on, we'll refresh our data here. So as we showed before, this is the views interface. And if we, let's get back to the game real quick and pause it so that we don't lose where we're at. So back in the views interface, we want to import from our newly created file for this flight, which is the latest file in the folder.
I'm going to cough.
All right, and so we got that in, and now you can see we're at the very beginning, right? We just started the countdown. We've got all sorts of strange values here. They look very large. They've got a large difference, but really it's a very small difference on the scale. This is 5.6 to 5.66, or 5.65. So this is 0.05, so this is 5 centimeters in altitude. And the reason you're getting this noise is because when the game drops the spacecraft, it drops the spacecraft just above the surface and it lands and then settles out. And it's, for some reason, the launch pad on Luna, the default one, is on a hillside. Probably not a great place to launch something from. So let's get this reloading automatically. And I'm not sure. I haven't looked into how you define all that. I believe it's all just XML documents, so it should be readily redoable. All right, get back over to game view. And we'll turn on our new data viewer here in the corner. So, and let's go ahead and let this run right up to the countdown, just to make sure we're getting new data. All right, so what these 3 or 4 charts are, there's only 3 that are useful to us. Here's your altitude above ground level. And you can see when we were first dropped, we dropped down, and then it bounced back, and it kind of stabilized. And I think this is actually somewhat the kind of effect you would see in an actual Kalman filter. So I think our values are actually already going through all this filtering from the game engine. Not because they're exact numbers in the game engine, but because the game engine's trying to be realistic, and these numbers start off unsteady. So here's our vertical speed as well. We originally, like I said, you can see we're at negative. Can you see the little blue cursor under there? I don't know. So here's a little blue cursor.
Oh yes, barely.
Yeah, and it's just barely right there. So this is negative 0.3.
You can't see it over there.
Yeah, well, so anyway, our vertical speed starts off falling, and then we balance out and we wobble around and then stabilize, and then we get this nice clean value. So I think they are trying to provide some realism in the sense that your data values aren't just absolutely rock solid all the time.
Right.
And the only reason we see this is because right now in the beginning, we're seeing this little tiny amount for each one. This is between 0 and 0.6 meters per second for the lateral speed. This is negative 0.3 to positive 0.3, so very, very small numbers. This is all what we would call the noise, or in the noise. If your numbers don't change more than this, then they're, quote, in the noise. So, let's go ahead and let her take off. Here we go. And then, of course, all the little tiny numbers just get smooshed away in the chart. So now our top one is what it was before. That's our altitude above ground level. Cruising up past 15, 17. Our next chart is our thrust, which of course we just fired very briefly to jump up in the sky. No, sky
this
here.
Is really way more.
And then our vertical speed, this is showing you how we're slowing, we sped up and now we're very slowing down at a nice consistent rate, which is based off of the local gravity. So this would be a steeper decline in the vertical speed. But this is Luna, yeah. So here we're crossing 4,000, but our vertical speed is below 50.
Yeah.
So it's not likely that we're going to make it to 5,000 in this coast. And then the PID's going to kick in and overreact and shoot us up into the sky. I keep saying sky like there's an atmosphere. So that's the other reason why things are behaving differently here is on Drew, we had an atmosphere that was adding additional drag and was slowing us down on our ascent. So we needed a stronger number. There we go. There's our attempt to get to...
this is going to land... Oh, there it goes up. Yeah. Past 5,000. So this is going to land on Luna.
Yeah, it took off from Luna. So
that's not what I said. Lots of things can take off from anywhere.
But yeah, it's not going anywhere near fast enough or high enough to make its way off of Luna. But now you can see our this one down here.
2,000 feet.
Right? So that's the thing. Because we overreacted when we were slightly below 5,000, we were almost at 5,000, but we overreacted.
It has no atmosphere.
Partly because it has no atmosphere, that certainly exacerbates it. But also because the PID is really tuned for landing, not taking off.
Right. Well, that too. Right.
So, and we could change that, but it hasn't been an issue so far.
That could be changed.
Yeah, certainly. We could put in different PID values for different stages, and then clear the internal PID values. Oh, yeah. Here's the glitch that we were talking about earlier. See, we're at 14,000.
Yeah.
We're coming up on 15,000. Yeah. Come on, here we go. You're gonna do it, and we're at 20.
Oh.
So
why did it do that?
I don't know, and it seems to
fires.
Yeah, and our vertical speed, our other speeds did not change. Our lateral speed is slowly decreasing, but our vertical speed didn't change abnormally. And this apparently only happens when you're pointed straight up and you're going straight up. I have coasted up at about a 45-degree angle and crossed 15,000 and gotten to like 16,000 and then came back down. It didn't do this. So I'm not sure why. I don't know if it's intentional. But you can see that's why the PID kind of tweaked right at that point. I can't quite see. Or I should say, it won't do it on the way down either because it's so far above 5,000 now. So now our vertical speed's finally going negative, which means we're finally actually falling back down to our 5,000 altitude. And when we get there, we're going to hover for a little bit, right? We hover until we hit 10% fuel, and then we drop out and land. But when we get down there, what I want to do is simulate what happens when you would be coming out of orbit. So you'd be retro firing to slow down out of orbit, and then you would stay locked retro all the way down to the surface, right? Now, then there's all this debate about whether you go straight down to the surface in a suicide burn, or you go down to the surface and on Luna, I would highly recommend going down to the surface, like, say, I don't know, 100 meters or so. Hover at 100 meters and look around. That's what that LiDAR was for. Get down to 100 meters, maybe 50, and look around where you're at and see if you can find a decent place to land, and you still have some time to hover and move around. And so there we go. We get this weird little stove top. I don't know what that is.
Like an alien top.
I'm not sure. A little capsule cap.
Right.
But here we're going to come crashing back down on 5,000. Once we get hovered, I'm going to set the heading to get out in this nice little grayish area that looks like it's not quite as nasty as this bumpity area here, right? We don't want to land out in that field of things to land in, of holes to land in. We want to land out there, and right now we're pretty much above where we started. In fact, we're over this crater, which we don't want to land in this crater, right?
Right.
So now that we're hovering, we're going to bring open the nav, and we'll do this manually. How's it? Yeah. I think in the end it looks more or less like a dialect as it gets skinnier here as we get more data.
Silo.
Top of a silo, sure. So we're going to go ahead and turn on the nav sphere and then use this heading. And while we're hovering, we're going to tilt over, actually pretty heavily. And now what this will do is, because we're not pointed straight down to the ground anymore, it's going to take more thrust to stay in the air, right? Or to stay at 5,000. And so as we burn more thrust, we increase this lateral speed a good bit, right? Over here, this bottom chart, we are accelerating a good bit, so this should help simulate what happens when you're coming in from orbit. Now, we're not accelerating too quickly for the first try. And later on, we'll modify this. Let's get it all the way down here. And then we're probably about to fall out of the sky. We've got a nice, decent lateral speed, 50 meters a second.
Side of a hill?
We don't know yet. But there you go. There was the end that was the fuel marker. And this was always part of the original program to point the rocket retrograde. We just never really saw it do it because we were always coming straight up and straight down through most of our testing. So this looks like it'll be a better landing area.
Maybe.
At least. And we're doing about 30, so until we actually hit that 700-ish mark, when we actually try and slow ourselves down, because remember, there's nothing in the calculation that says that your pitch is this, and therefore not all of your thrust is being used downward. It's being used at an angle, and therefore not all of your thrust is pushing you back up. Now, conveniently, the PID algorithm handles all that automatically for us. As far as still firing to stay in the air, it just fires more because it needs more. And then the rest of the guidance that was already existent in the game is handling keeping us retrograde. So here we go, 400 meters, 300 meters. Notice how quickly our lateral speed has dropped.
We're almost out of fuel.
Well, 7%. We got a lot of fuel left because it's Luna.
Oh, there it is.
And doop, and wobble. Don't fall down. So you see, we have this weird shape to our altitude curve. So I'm going to go ahead and submit this at some stage.
What is that?
I don't know. And it's weird because if it does it at anything other than straight up, it doesn't seem to have that side effect for some reason.
Done that anyplace else?
It did it No, as far as I know, I haven't seen it on anything other than Luna. So
maybe it's lunar centric.
Luna-centric. It might be. So, I mean, it, in real aircraft, as we discussed in the previous video or two ago, the radar altitude is maybe 2,500 feet is the max height for the radar altitude,
Yeah.
which roughly speaking, divided by 3 is maybe 10,000 meters at most, somewhere in that range. And divide by 3 all that quickly in my head. Um, so the idea being that the plane doesn't come down as rapidly as a rocket. In general, it's coming down at a 3-degree slope, 3 to 4 degree slope instead of nearly vertical. Um, so you don't really need to know if the ground is more than 2,500 feet below you, as long as it's below you, right?
Right.
And so I guess the point being that um, if you simulate to simplify the simulation, if you're 1,500 feet above the surface, do you need to simulate all the complexity of the actual surface, or do you really just say, okay, well, about here, and you make an artificial ground level that's above all possible surface features? Like the highest point on Earth is Mount Everest,
Right.
right? If you go, 5, 10,000 feet above that, whatever that would be, about 40,000 feet or something. No, I don't think it's that quite that bad. But anyway, if you go a few thousand feet above Mount Everest and you say that's the sphere of the highest points on Earth, uh, as long as you're above that altitude, you don't have to worry about the complexity of the actual terrain. Well, everything gets simpler, right? And you just stay above that level, and you're never going to run into anything on the Earth. So maybe it's something like that. It's you're above 15 kilometers. Who needs the details? And then it might be a glitch. I don't know. So, in any case, let us go back in and what we want to do is we want to make a couple of minor changes. We want to shoot up a little higher so that we get above 5,000 on that first ascent, and we have lots of time to hover, and that'll give us lots of time to get somewhere, right? Yeah. Otherwise, dang it with the rights. Correct. So a couple of things we're going to do differently. Let's see. First off, on our target apo ascent, instead of pointing straight up, we're going to be very aggressive and we're going to point over. Let's see. Probably don't want to do as much as or as little as 45. Let's maybe do a 60-degree pitch. So that'll initially throw us in some direction when we first take off. And then because the hover algorithm doesn't change our pitch once we get there, if we blow past 5,000, we'll come back down. Everybody just imagine this is the exhaust plume. All this hair is the exhaust plume of the rocket. Here's the rocket base, and here's the rocket nose. See? Makes perfect sense, right? So all the hair is the exhaust. So by taking off at 60 degrees, we can sort of plan where we want to go and not have to, or rather, I should say, we'll stay at 60 degrees in our hover, and that'll burn more fuel because we're not pointing straight down. And so we'll get a completely different set of graphs. That's the other thing we're going for. Plus, I want to get to the point where we're going pretty good speed. Right now, we were doing 50 or 100 lateral speed, 50 or 100 meters per second lateral. Right. That's not what you're coming in out of orbit at, right? You're coming in out of orbit at whatever, slightly less than orbital speed, which for this moon, we could look it up, it's probably in the 2,000 meter range, or maybe less. 1,500. Anyway, somewhere there's a documentation as to the escape velocity of Luna. You just have to be slightly less than that. and then you'll come in, and since there's no atmosphere to burn up in, you can cruise in nice and smooth. So we're going to take off. We're going to aim at 60, and what we'll do is before we actually take off, we'll set our heading to decide which direction that 60-degree angle will be. And then the one other thing was 1.3 is not quite enough. We need 1.3. It was 1.33 for Drew. Let's make it 1.34. So it's almost the same value. And the only reason I remember any of these numbers is because we keep putting them here in the notes when we put in start the log. So this would be roughly what we did on Drew. This should get us right up at 5,000, although maybe not with the 60-degree angle. We'll see. Hopefully it'll get there and we won't overshoot like we did last time. And then we'll have a chance to cruise along. We'll eventually get up to I think we can probably pitch over almost completely, like way down to 30, and that should give us a whole lot of lateral speed while we're trying to hover. So we're going to fly and stay at 5,000 while we go forward through the sky. Again, not something you do when you have an atmosphere. I don't know if it's again. I don't know if I said that once before or not. But in any case, so again, no noise. Okay, everything. The only other thing I changed before was this minimum for the minimum thrust. 1% thrust on Luna actually shins you in the air, so I had to make it even less. But interestingly, the PID values are otherwise the same. Now, while this gets over there, one of the questions, or one of the requests that we've had was for a tie-in to from this to Simulink from MATLAB, and I got MATLAB, used it years ago. I got the 30-day trial. Like I said, it's not terribly expensive, but it's like using, sometimes it's like trying to use a jackhammer to hang a picture, right? It's a complex and extensive tool set that does far more than I need it to do right now. I just need 4 strip charts, right? So that's why I'm sticking with views right now. Now, I had an interesting set of issues. So MATLAB came first, or was the original. Then Simulink came up, and I think it was a separate company, a separate product from a separate company, and they merged. And so they're tightly integrated, but they're not from the same mindset. They're not built on the same mindset. And so in MATLAB, I could import the comma separated file, like I'm doing with views. But I couldn't import it in Simulink live as it gets updated unless I happen to have Microsoft Office installed. So go figure why MATLAB can read the file fine, but Simulink can't do it unless it has Office. And I'm guessing it's because of the idea that they don't want to reread the whole file each time. They just want to get the last line or the latest line that was added, and you can do that kind of thing by scripting Office. So that might be the what's behind that. But I messed with it for about 4 hours, and I said, well, I'm going to have to read finally have to read the directions, right? 4 hours of Google searches and trying to do what I wanted it to do. It's just not really set up the way I imagined it was. So what we would probably have to do to get Simulink working is, as part of, add the Simulink libraries to the plugin code that's being used here inside the game. Now, the plugin code's in C#. Most of the APIs were designed for C and C++ in MATLAB and Simulink. I don't know how that mapping works necessarily. Maybe it'll work. Maybe they got C#. I'd have to double check. But all that is to say that doesn't look like Simulink's coming anytime soon. Not since it really isn't necessary for what I'm trying to accomplish here. And I also don't want to necessarily, like I keep saying, I want to use tools that are available to other people and not you know, demonstrate things that are necessarily proprietary. Um, just from the general availability standpoint. So, having said all that, let us get our charts reconnected. I unfortunately could not quite say all that whilst getting the chart done because it's a little hard for me to do 2.5 things at once. And specifically, it's that half thing. Doing the 2 things, that's fine. But once you add the extra half, it gets a little crazy. Alright, so there's our data so far with our initial noisiness. And let's see, make sure we got the reload going. Without it, it's not nearly as interesting. And, oh yeah, the other thing. We are stopped here at about 5 seconds. Let's take a look around. We want to go that way. Well, more or less towards Earth. We want to get off this plateau and get out here in the distance. Here we are right here, just barely, right in the center of the screen. You can barely see us. But I want to get over there to land. And I also thought it'd be interesting to see, you know, we're hovering at what we call 5,000 meters above ground level. We're clearly at a higher point right now than we would be if we go over here. Are we suddenly going to become 6,000 feet above ground level? As the hillside falls away from us, do we follow the hillside and stay 5,000 feet above the hillside? I don't know. I haven't checked that. Well, it's also kind of hard to tell because I don't have a camera that is static. It's always relative to the craft, so it's kind of hard to see it doing that kind of maneuver. Just like it's kind of hard to tell that it's hovering, right? So
right.
You
just said that. See.
Enough with the rights. Okay, so we're going that way. Comprende?
Yes.
So to do that, we want to go, well, a little bit less than due east. Roundabout heading 120. So we're going to go in the direction of the straight blue line. And that gets us off the plateau and hopefully into a flatter landing area. So we'll leave this up when we launch so you can see the adjustment made by the launch algorithm. And let's see, here we go. Away we go. Yep, there's our pitch over. Cruising away from the Pittsville. Let's see. Once we hit our, hopefully we'll come pretty close to hitting the target altitude of 5,000 on this ascent, and then once we get there, we'll start trying to hover, and then I'm going to slowly pitch it over more and more until we get maybe down to about 30. I want to add, well, this is part of the problem. If I'm at 5,000 and I'm going really fast laterally, I may not have enough time to brake and get upright before I run out of altitude. It looks like we do cross 5,000. Yay! So we're not going to overshoot. We're just going to start coming down once our vertical speed here. Vertical speed. Here. They are labeled on the side. It's a little hard to read if you tilt your head. There's lateral from the bottom up. Oh, there we go. Oh, I guess it did reset itself back to vertical. Alright. Well, we want you... Let's go to 45. Now we should start throwing extra thrust. Oh, we're still above 5,000. So once we come back to 5,000, there we go. We're probably going to see all sorts of wobbly thrust lines here as we try and stay at 5,000.
There it is on the second one.
Yeah. And then our lateral speed, we're crossing 80. So our lateral speed's, increasing just in little spurts. As we throttle to stay above 5,000, that also pushes us faster, right? And I'm not sure how far over I dare tilt us. But I think 30 was the danger zone. We're gonna fly into...
You don't own the thing.
Can't say it. Can't sing the rest.
No, you don't know the...
Three? Is it 3? Is it 3 notes that I get?
Probably. Let's not push it, whatever.
Yeah, whatever it is, we're not gonna push it. YouTube's algorithm might just figure it out. Now we get really spiky response.
Oh boy.
Because we're not, most of our thrust is being expelled, making us go faster. We're getting pretty fast. We're going up in the 250 range. We got 4% of fuel, 4% of fuel left before we... Oh no, we're going to fly into a crater, it looks like. After all that planning. Well, not really, but... So this is where, if you were going to do this flight in reality and you were trying to get from point A to point B on the moon, traveling, taking some stuff from, I don't know, oxygen producer on the polar area. There's water and or ice in the shaded parts of the craters on the moon in the polar regions. So you land in the polar region, you melt some water, and you do some electrolysis. You get yourself some hydrogen and oxygen, and then you compress that into a cylinder, and now you want to get that to someplace else. Well, you would do a much more straightforward flight. You wouldn't be hovering at 5,000 through your flight. You would just fire enough. Whoop, there we go. You would just fire enough and in the right direction and at the right angle. Right? Correct.
Yes.
To make your nice parabolic flight. You wouldn't want to have to burn a bunch of fuel staying upright or staying at a given altitude. You would just want a nice parabolic flight from the lunar pole to wherever else your craft is going to land. So we can get rid of this now. And you note we've got retrograde locked. So we're going to stay pointing our engine in, well, we got a pretty decent speed, 471. Surface speed, I don't know what that makes out in miles per hour, but 158 was about 350 miles an hour, so had 4 times that. So we should be doing about 1,200 miles an hour, perhaps. Pretty fast. So this might be close to what as you come out of orbit. A speed you might be encountering coming out of a sort of minimal orbit. Because that's what we're getting back to. We've done a lot of time on the hopper and the lander and the PID, and that's all well and good. But we got to get back to our original craft that managed to make it into lunar orbit and gave us a satellite. But then we want it to land. And that to be fully automated and nice, smooth controls and so forth. So that will be what we get back to here shortly. But here we're coming in. We're only 900. Ooh, it's coming in fast. I don't know.
Oh, that doesn't look good.
Well,
it's got a big thruster there.
It didn't break. It didn't explode. Gotta have a parachute, right?
Oh, there's a parachute.
Well, it didn't break, but
Oopsie.
this is why you probably want to land at maybe, right now we literally were hovering and then we targeted 0. So this is why you want to maybe target 100 meters would be our landing program perhaps. We come out of orbit, we target 100 meters, we figure out where we can land, have enough fuel to hover slightly, and then finally do our final descent to the surface. I think that's going to be the better plan. And like I said, next time that is the goal is to get back into the entire trip from takeoff on Drew all the way to landing on Luna, fully automated, and we'll get back to that. We may or may not save our boosters, but really that just means there's fuel you got to leave behind in your booster. So I hope you enjoyed this quick review. When I keep these things a good bit shorter and sweeter, you'll
Thanks,
note
everybody.
we're still recording data. So you'll note our elephant here isn't too horrendous.
It's not an elephant now.
Well, no, not really.
It's more of a mountain. It's that thing we saw last night.
A plateau or something.
Pile.
Maybe if it's from the side, it's a bunt can. Bunt cake pan. Ish. Bunt can, yeah, I don't know. Anyway, it's an upside down bowl. But you can see, just by setting ourselves retrograde, we were able to slow ourselves down reasonably well. Clearly, we didn't quite succeed. So,
oh well.
We'll try again next time. And then we'll get... maybe we'll do that. Or maybe we'll hop around the moon a little bit more. We'll see. Anyway, hope to see you next time. Feel free to like, subscribe, link, ring the bell, all those various social media things. And we'll see you then.
Bye.
Take it, button, yeah!